In machine learning, uncertainty quantification is not a luxury, it's a necessity. Whether you're deploying models in healthcare, finance, or autonomous systems, knowing how confident your model is in its predictions can mean the difference between life and death, profit and loss, or safety and risk. The gold standard for uncertainty quantification is conformal prediction, a principled, distribution-free framework that guarantees coverage. Your prediction set will contain the true label with a specified probability, say 90%. But here's the catch. Standard conformal prediction breaks down when data is missing. Missing values are everywhere: clinical records, sensor logs, survey responses. And they're not just inconvenient, they fundamentally distort uncertainty. When features go missing, the distribution of the data shifts, and standard conformal methods fail to maintain their coverage guarantees. Worse still, most existing methods assume the missingness is completely at random, a strong assumption rarely met in real-world settings. In practice, data often goes missing because of the values themselves. A patient skips a blood test because they're feeling unwell, or a sensor fails under extreme conditions. These are missing at random MNAR, or missing not at random MNAR mechanisms, conditions that invalidate traditional approaches. So how do we fix this? Enter Mask-Conditional Validity, MCV, a more refined and realistic goal. Instead of just ensuring overall coverage across all data points, MCV guarantees that the prediction set is valid conditioned on the specific pattern of missingness. That is, for every possible configuration of missing features, say, features 1 and 3 missing, your prediction interval should still contain the true label with high probability. This is crucial. Without MCV, you risk undercoverage in critical subgroups. For example, a model might be confident when only one feature is missing, but fail catastrophically when multiple features are missing, exactly the scenarios where you need the most confidence. Yet current methods have serious limitations. CP-MDA-Exact only uses calibration points with fewer missing values than the test point. In small datasets, this can leave you with no data at all. CP-MDA-Nested fixes this by artificially adding missing values to the test point, making it more conservative, inflating prediction intervals and wasting information. We needed a better approach, one that's valid under any missingness mechanism, doesn't require modifying the test point, and produces tighter, more informative intervals. Our solution, the Preimpute-Mask-Then-Correct framework. Here's how it works. 1. Preimpute the calibration data using a distributional imputation, like multiple imputation by chained equations, mice, or Bayesian ridge regression. This fills in missing values with uncertainty, creating multiple plausible versions of each data point. 2. Mask the imputed calibration data using the same missingness pattern as the test point. This aligns the calibration data with the test case, enabling conditionally valid prediction. 3. But here's the key insight. Imputation introduces a distributional shift. The imputed data doesn't perfectly match the true underlying distribution, especially under MNAR or MNAR. So simply applying standard split conformal prediction now risks undercoverage. That's where correction comes in. We introduce 2 novel correction mechanisms. First, Mask-Conditional Weighted Conformal Prediction. We reweight the calibration points using a likelihood ratio, the ratio of the true conditional density to the imputed density, given the observed features and the missing pattern. This weight adjusts for the shift. Points that were unlikely under the true distribution get downweighted, while those consistent with the truth get higher influence. The result? A weighted quantile that correctly accounts for the mismatch. Theorem 3.3 proves this guarantees mask-conditional validity under any missingness mechanism, MCAR, MAR, or MNAR. And because we're only imputing the calibration data, never the test point, we preserve the original test input, avoiding artificial distortions. Second, Acceptance-Rejection-Corrected ARC, conformal prediction. This is a more efficient alternative. Instead of computing weights, we use an acceptance-rejection sampling strategy. We draw calibration points from the imputed dataset, but only keep those whose likelihood ratio is high enough. Essentially, we accept only points that are plausible under the true distribution. The accepted points now form a new calibration set that's exactly distributed like the true conditional data, given the missingness pattern. Apply standard split conformal prediction on this clean, corrected set, and you get valid, tight intervals. The beauty of ARC is speed. It avoids expensive grid searches and complex weight calculations. In our experiments, it ran 90% faster than weighted CP, making it ideal for real-world deployment. Now, what if the likelihood ratio is estimated imperfectly? After all, we're using a classifier to estimate it, like a histogram-based gradient boosting tree. We analyze this in depth. Theorem 3.6 shows that even with imperfect estimators, the coverage remains controlled. Crucially, we find that you don't need perfect accuracy, just the right relative ordering. As long as the estimator preserves the ranking of likelihoods, coverage stays near nominal. Empirically, when the correlation between estimated and true likelihood ratios exceeds 0.3, coverage stabilizes at 90%. This makes the method remarkably robust to estimation noise. We tested our methods on synthetic and real-world datasets, concrete strength, bike sharing, and a large medical expenditure survey. On synthetic data with 50% missingness, our methods reduced prediction interval width by 30% compared to CP-MDA-Nested, while guaranteeing MCV across all 1023 missingness patterns. On real datasets, ArcCP reduced interval width by 12% on concrete data, 7.5% on bike sharing, without sacrificing coverage. Even under MNAR and MNAR, where other methods fail or become overly conservative, our approach maintains valid coverage. And when we remove the correction step, just pre-impute and apply standard CP, coverage dropped to 89%. A small deviation, but enough to break guarantees. This proves correction is not optional, it's essential. So what's the takeaway? Conformal prediction with missing data isn't just about filling in gaps. It's about understanding how those gaps affect uncertainty. Our Preimpute-Mask-Then-Correct framework, backed by 2 robust correction methods, delivers guaranteed mask-conditional validity under any missingness mechanism, tighter prediction intervals, up to 30% narrower than prior methods, compatibility with standard imputation pipelines, no need to retrain models or modify test inputs, robustness to imperfect likelihood ratio estimation, efficiency, especially with ArcCP, which is fast and scalable. This is a major step forward in uncertainty quantification for real-world data. Because in the end, the goal isn't just to predict, it's to predict with confidence, even when the data is incomplete. And now, for the first time, we have a method that delivers on that promise.